So yeah, I'm Sepand Kashani from the EPFL Center for Imaging. We are not a lab. I will make that clear. Our job is not to write papers. Our job is really to support research labs at EPFL who have needs in imaging, either image analysis or image reconstruction, so that they can do their research more efficiently. So basically, we develop software and training material for them as they need it. So Eric mentioned at the opening of this day that the goal is really to show you what type of image or what type of open source tools exist for doing optical imaging so that you can better control your imaging pipelines. And in that respect, I will talk about Pyxu, which is a library that we are developing at the Center for Imaging, which its main goal is really to help us support the imaging community at EPFL to do any type of image reconstruction. So maybe before I dive into the library itself, I'll give a bit of context of what we're talking about. So this is a library to do computational imaging. Essentially, I mean, there's always something out there we are trying to look at, but we cannot observe it directly. So we have sensors that capture stuff it emits, whatever it is. And then we're using a computer to try to get back the quantity of interest we had that we are interested in. And typically this stuff that is emitted, it's in some form of wave, anywhere in the spectrum. And therefore, there's both the hardware part and then there's the computation and the software that you need to use to do the reconstruction. So I'm assuming most of you are from an optics background, so this will not be surprising to you. When we have a camera, we have the radiance of the scene we want to capture, and then what you actually measure in the camera is not the original scene. It's a pixelized version of it through a Bayer filter that's blurred, et cetera, et cetera. And so here we use computation to try to undo where's the mouse? Okay, no mouse. We try to undo the blurring effect and the color effects to get the image. So this is optics has the benefit of having the data that already looks like an image. So it's a restoration problem, but there are other modalities depending on the wavelength you're looking at where what you are measuring is not at all an image per se. And one of those is tomography with X-rays. So here the concept is you have like a cylinder of concrete that's sitting on a turntable here on this X-ray machine, and then you have a X-ray cannon that shoots rays through it, and you try to reconstruct. So you record these 2D projections of the object, which are 2D images, and you want to reconstruct the 3D volume of the insides. And here we definitely need to use a computer because we're going from a 2D domain to a 3D domain. So this is one domain in the X-ray regime. Now, if we go more higher into the radio spectrum, you have another type of imaging instrument where here you have dish antennas that are looking at radio emissions. And typically, you are trying to look at stars, either galaxies or remnants, well, black hole shadows here. And what you measure is time series, not at all an image. And here also the complication is going from these raw signals back to the signal of interest, the image you're interested in. So why am I talking about all these different stuff? Well, it turns out that irrespective of what these domains are, essentially, I mean, it's always a wave equation or something similar that is defining how our information is going from the object we're looking at towards what we are sensing. And therefore, the same type of mathematical model exists and is shared between all these domains. Typically, you're either trying to compute some type of Fourier transform, some type of line integrals, convolutions, very basic operations. And these operations appear in every domain, basically. So now, what's surprising is despite the math behind most of these imaging problems being very similar, on the software side, it's a different game. Basically, We have a huge collection of software available in the community. People who do X-rays have their reconstruction pipelines and their specialized software. People who do MRI or astronomy have their tools, optics as well. And so that's very good. I mean, we have a lot of choice available, but the software is very siloed away. Every domain does its own thing. They have their own software solutions. Part of this is historical. I mean, they didn't all start at the same time, so it made sense for them to develop their own tools. But at EPFL, we have a very rich imaging community that does pretty much everything. And as the Center for Imaging, we need a tractable way to be able to support them all in their imaging tasks without exploring all the libraries and dealing with their incompatibilities, etc. So we also want to have tools that let us accelerate this R&D process so that we write, or domain scientists write less code, but can reuse components easily across different applications. So that's where Pyxu comes in. This is a software library we have developed at the EPFL Center for Imaging. And essentially, its goal is to regroup the computational part that is common in all these imaging modalities. So it's really a library of all the core mathematical operators that appear in imaging modalities: Fourier transforms, non-uniform Fourier transforms, X-ray transforms, convolutions, all of it working on CPU, GPU, even the Google TPU, so that's nice. And the idea is really to try to put this computational core in common so that when we improve these methods in the library, they can easily disseminate to all the fields who use them and not have to go add a new technique in every domain-specific tool. So it's quite lightweight. We've been developing this for 4 years now, and I've dog fooded it a lot during my PhD, so I know it works. And yeah, over the years, we've gone through multiple versions. Now we have V2 that's released. And if you go on our website that you cannot see, yeah. So we have a website where we describe really the tool, and you have even example galleries of different type of applications that you can tackle with it. We are constantly adding new ones. And then we also have the extensive API reference, which is available. So people who have an image reconstruction problem, or not interested in reconstruction, but you just want to use some mathematical operation that we have, you can just come read it up and use it as you wish. So right now we are developing the V3, which should be released in the next month or two. And I would say the main change compared to what you will see on the website is that we are having even deeper, how to say this, deeper interaction with the deep learning tools that exist out there, so that you can really use these and easily plug them into whatever framework that is out there for more advanced reconstruction. So I won't go too much more into the detail in the code here, because we will have the workshop in the afternoon where we'll go through a deconvolution example, where you'll get the feel of what the API looks like. And yeah, we'll be using the beta version of V3. But perhaps to show how useful it is, I will now show you an example that we tackled a few months ago in one afternoon in tomography. So at EPFL, we have this expensive cone beam tomography machine that is used to look at the insides of these concrete cylinders. And this device comes with a cool software that lets you reconstruct the volume in semi-real time on GPUs, etc. So it's really good. But if you want an image, or you want to reconstruct the image differently than what is provided by the software, you're out of luck. And so what we wanted to do is see, can we try to obtain this type of image that the software gives us, but by throwing away 75% of the data because we want to speed up the acquisition. But by doing so, we need to now look at different image reconstruction methods than the standard one that they use. And so what did we do here? We just took the raw data that came out of the machine and the XML file that describes what it's scanning, the rotation of the table, etc. And we were able to create a digital twin of this scanning process using the X-ray transform tools we have in Pyxu. So we have basically the scan patterns here. This is one slice of the raw data. And then this roughly took us 2 hours to go from parsing the XML file, figuring out what it is, and getting our first image, the one in the middle, by just doing the dumbest thing possible. So that was very good. Normally this takes a few weeks if you want to start from scratch. And then now that we have this first image and it looks decent-ish, we can now try to improve it to get better image reconstructions. So the first thing we did was saying, okay, instead of just doing the back projection, let's actually try to invert the X-ray transform that is being done by the instrument. That's typically a few lines of code in Pyxu once you describe the geometry. And when you do that, we already get this image, which, okay, up to a rotation is the same thing as the device gives us, which is good. So here we still kept all the data, but now that we replicated it, we can now do what we wanted to do. So now we throw away 75% of the data, and let's try to use the same algorithm. We see that by doing so, okay, it does break down, which is to be expected because this method only works well if you have a lot of data. We have these high frequency artifacts that appear. And so instead of doing, this type of closed form formulas to do the inversion, we now tried something else in Pyxu. We said, let's try to just do regularized inversion, least squares, as a first solution. That's also, again, a few lines of Pyxu code. You just call the pseudo inverse of your operator, and then you get this, which is already better. And then, okay, you can add some regularization to smooth it out, but it's still grainy. And then you can use more regularized inversion methods by just saying, I know the image is in the center, the background is black, etc., etc. And by doing so, again, by just adding a few lines of code and tweaking your optimization problem, you can get progressively better images. And then beyond this, you can add more like total variation regulation. This, okay, it's better or worse, that is up to the scientists to decide, but basically we can do these type of image transformations very quickly. And everything I've just showed you now was really 1 afternoon's of work, which would take much longer in general. So, and then, yeah, you can also use more AI-driven methods like plug-and-play methods to improve the image reconstruction. And here we just took a off-the-shelf denoiser and replaced part of the reconstruction algorithm, and you can really mix and match tools from the deep learning research and conventional optimization to get our images. So I was a bit fast, but that's actually more or less all I have to say about Pyxu. So it's really this, we see it as a useful tool for any type of image reconstruction problem, or just as a computational toolbox for your tasks. And this afternoon, what we will see in a deconvolution example is how can we craft our problem in Pyxu, which is fairly simple, and then how do we plug that into standard tools that exist in the deep learning ecosystem to actually do the image reconstruction after that.